at Maxim Design System. Okay, so just a general outline for this presentation, which include the about section, products, syntax flow, and applications. Um, so the company general about section includes the Maxim Design System is a leading simulator solution provider company dealing in the simulator device modeling, silicon photonics services, and softwares. So MDS established in 2020 and partnered with Nextnano, Star Photonics, and Nanolabo for atomistic simulation as well. Okay. About Nextnano is a widely used software for electronic and optoelectronic simulator device simulations. General applications of Nextnano include nanotransistors, LEDs, laser diodes, quantum dots, which is mainly used for the quantum computation. Nanowires, quantum cascade lasers, HEMT, photodetectors, and solar cells are, the major application area in which the Nextnano is very much useful. Coming to the product sections, so Nextnano include Nextnano Mat, which is a graphic user interface. Along with that, it include the Nextnano Plus, which is basically a Schrodinger-Poisson current solver, written in the C++ language. And it is also having the Nextnano 3, which are more comfortable on the Fortran. Nextnano MSP was, the NEGF code for quantum transport based multi-scattering vertical probe model. So previously, it is mainly used to simulate the resonant tunneling diode and quantum cascade laser. Previously, it was a part of a separate bundle along with the Nextnano.NEGF, which is also used for which is NEGF code and used for the quantum transport based upon the non-equilibrium gain function method. So previously these two are clubbed together. Just a second. Okay, these two are clubbed together previously for the NEGF bundle, and these two are to simulate the normal transistors, the nano devices, and the qubits. Okay, but right now, what they did is just include these three together. So currently, you are able to simulate the resonant tunneling diode and this one, the quantum cascade laser as well, using the Nextnano.MSP. Okay, this one is a separate bundle, so you don't need to care about this. Okay. Now coming to the syntax flow. So the syntax flow is very systematic. So it starts with defining the global variables. Then you need to specify the simulation dimension. After that, you need to specify meshing. Then after that, once you specified your meshing, then you need to define the structure. At which particular point, which material you need to place, and what are the different regions, what is the impurities you want to specify, then where your contact exists. So these kind of statements, it is included in the structure section. Then after that, we have the models which specify the functionality of the device. Okay. For example, there are Schottky Red-Hall recombination models which specify that electron holes are recombining. So this kind of a functionality, different models, mobility models are there, okay, which used to specify the functionality of a device. Then method and the source section, that what kind of methodology you want to use for simulating, whether it is quantum, whether it is a classical. Okay, then comes to the output statement, which is specified by the run statement. Okay, then a little bit of about the convergence issues that you can resolve, while setting up your code. So it's we'll discuss that part here. Okay, now talking about the global variables. So usually because there are two codes, so mostly we'll be discussing about the Nextnano plus. Okay, so for this, these symbols are most commonly used, okay, to specify the constants, you can say, in the starting phase, so that later on you can use that particular value again and again. And if suppose you need to modify also, you can modify in the starting phase itself, so that automatically, in the other places it will be modified, and it will reduce the complexity of your code as well. So in that particular sense, to reduce the complexity, global variables plays an important role. Okay. Now coming to the simulation dimension. So first you need to be clear about what simulation dimension you need to use and why you need to use. And one more question comes to your mind, that which simulation dimension you should prefer, before simulating any device. So first I'll tell you about like where you should use the 1D simulation dimension. So before that, I would like to come to a particular thing, that is how you should visualize, that how you are simulating, how your structure will look like when you fabricate, and that kind of a stuff. So as you may know about the silicon wafer, so we start with the silicon wafer, right? So which will be in the round shape. Then we have a particular diameter which is specified by like 6-inch, 8-inch wafers, and then 12-inch wafers. So most of the companies which are working on the lower dimension, like 180 nanometer, they are using the 8-inch wafers, and which are going beyond like 55 nanometer. So they are using the 12-inch wafers. Okay, now if suppose your device, like this is a top view of the silicon wafer. Suppose if you want to see the wafer, like how we are simulating, so I'll just take this particular point as our device. Okay, so if I take the thickness point of view of this particular, so suppose it's like a cake, and you cut a particular, of this part of the cake, then somewhat it will look like this, right? And this is my top view, right? Okay. So what we are simulating is, suppose we are talking about a MOS transistor. So here will be our junctions, because we are doing here will be our gate on the top, and you know, we have a gate oxide and gate on top of that. And now if I convert it into, kind of a x-axis, like the straight plane, so it will be like somewhat look like this one. This is my gate, this is my source, this is my drain, and this is my substrate. So this is a kind of a visualization point of view, that how you are creating your device inside the simulator itself. Okay. So maybe you have understood that how we are going to create a device in this. Okay. Oh, okay. So this is known as your cross-sectional area. Okay. Cross-sectional area. So we are cutting. We are just doing a cut line here, and then we are seeing the cross-sectional view of that. So that will become your device. Okay. So that kind of a cross-section we are creating here inside the simulator. Okay, now coming to the simulation dimensions. So three kind of simulation dimension you can use. That is 1D, 2D, and 3D. And yeah, so three type of simulation dimension you can use: 1D, 2D, and 3D. Okay. So where which dimension you should choose? So that's another question. All right. So suppose if you are creating a device, suppose initially we have a bare silicon wafer. Okay, without any doping. So doping is uniform throughout, right? So this is the length, and this is the height. Okay, so if we do a 3D simulation of this device, making a contact on the top or maybe in the bottom, right? It doesn't make any sense because if you take a 3D dimension, then the mesh points will be more and the computation will take more time. So instead of that, to see how the doping will look like, you can simply take a 2D view of it, placing a contact on the top, or you can take a 1D by making a cut line here, and it will be like this. So here, this part will be my contact, these two parts, and here it will show the doping concentration, right? That what is the doping concentration, maybe 1E14. So instead of going to the three dimension, when you have a similar structure throughout, I mean, it's of no use. It just increase your simulation, time. So it's better to use 1D in that particular case. Okay, even if you have the multiple layers in between. Just a second. Even if you have the multiple layers on the top, suppose if we talk about the any detectors with the consist of the multiple layers of LGAN or GAN, right? Different layers, like 100 layers. Okay, throughout that in the x-axis you have the similar dimension, right? So there is no point of simulating the 2D in that particular sense. What you can do, because you directly need to see how the band structure will look like, and what is the barrier height, and what is the this kind of things you need to do, and whether tunneling happening or not. So you can simply take a cut line over here, and accordingly you can start with that. Maybe later on you can do the 2D simulation, but it's good to start with the 1D in that particular sense. Where you should not use the 1D simulation, that's another part. Suppose if along the x-axis, your dimension, the concentration or things will differ, because along the x-axis, here we have a source doping, here we have a drain doping in the transistor, right? So throughout the concentration or the structure is not similar. In that particular case, you should start with the 2D. 1D not a solution. Okay, if just you want to see the MOS cap, then only you can take a 1D cut line, and you can try to check how much the electron concentration is there in the channel part, or it's depleting or not. So this kind of a stuff you can characterize. But to simulate the whole device, you need to do the 2D simulation in that particular case. I hope you understood with this 1D, 2D, and where you should use this. Now coming to the statement, which statement you need to use.
Abhishek sir,
Mhm.
can you please once again tell us like how 1D and 2D differs?
Yeah, yes, sure. So, okay, let us take an example of, you know, LED structure. We compare the LED structure with the MOSFET,
Okay,
right? Okay.
okay, okay,
So you have a silicon substrate here. Then
okay,
you have a multiple layer. You have grown the multiple layers using the molecular beam epitaxy or any other instrument, right?
okay,
Like maybe again GAN, AlGaN, multiple layers. Okay,
okay.
so up to N. Okay.
Mhm.
Now, if you simulate in 2D, because your contacts will be on the either on the top or the bottom side or maybe this side, right?
Okay.
Okay. So
Mhm.
the core structure is this part.
Yes.
If I can change the color as well. Okay. So your main structure will be like this is your main part, right?
Right.
Okay. So if you
Mhm.
simulate 2D, it doesn't make any sense because ultimately the main part which is contributing is this cut line, right? So
Okay.
whatever your work function is there. So if I draw a cut line, then it will look like something like this. Algan will be like your conduction band will be like this, right?
Mhm.
And in between you have a GAN, then Algan, okay,
Mhm.
then again GAN, right? So your structure will be like this, and based upon that, your electrons, once you apply the biases condition, then this will tilt down, and then after that, because of the
Mhm.
electric field, the electron can travel through the barriers. So that thing will happen. So if you draw a 1D, if you draw a 1D plot as well, that is good enough to characterize, the device.
Mhm.
But now I'll take a case of MOS transistor.
Mhm.
Okay, a similar way I try to draw. Okay, this is my silicon. Here is my source. Here is my drain.
Mhm.
Here is the gate aux, and this is my gate.
Mhm.
Gate, source, and drain. And here
Mhm.
is my substrate.
Okay.
Now, if you how you can define the functionality of the MOS transistors with the 1D cut line.
Mhm.
You draw a cut line either here,
Mhm.
okay, that will give you the MOS characteristic, not the device characteristic, MOSFET characteristics, right? IV characteristics you cannot extract using the 1D simulation. That is not
Okay.
possible because
Right.
that is beyond like two terminals, gate and substrate.
Okay.
Okay, or either you can take this kind of a cut line which will
Yes.
show you the doping concentration, you know
Okay. Mhm.
or maybe the drain and the source, source and the drain characteristics with the applied biasing condition.
Mhm.
Okay, but not the device because gate influence cannot exist in that particular part in 1D simulation, right? Because we have four terminals. Here
Mhm.
only we have two terminals, and between the two terminals directly we can take a 1D cut line, and then we can plot the results with the different biasing
Mhm.
condition.
That means symmetric structure
Yeah,
having 1D and
yes,
asymmetric having 2D.
yes, 2D, yes, correct.
Okay.
Okay,
Okay. Okay.
if suppose another example for the 3D. Now you have a FinFET.
Mhm.
Okay, I try to do. I'm sorry, my drawing is not that good. I try to draw it. Okay, suppose this is your FinFET with the fin here, and you
Mhm.
have a this kind of gate over that.
Mhm. Mhm.
So in that particular case, if you see through the x-axis, it's not symmetrical.
Mhm.
Z-axis, although it looks symmetrical, but you have a context here with the different shape, or
Mhm.
the spacers are there.
Mhm.
In front of the gate. Okay,
Mhm.
so in the Z dimension also it's not symmetrical. So in that particular case, we need to use the 3D. There is no other way. Okay.
Okay.
To properly model the device, I mean, you need to use this one. Okay. Understood. So now coming to the syntax which we need to use. So the syntax which is used is specified in the global statement and is specified by simulate 1D, then after that brackets. So this is for the 1D, and if you want to specify, then it will be like 2D in the two dimension need to specify, then it will be like simulate 2D, and if three dimension, then simulate 3D. Okay. Something more about this global statement is you are also specifying a temperature, this is a by default temperature. If you will not specify in this, that it will automatically take 300 Kelvin. Okay, that is 27 degrees Celsius. If you want to change, if you want to, simulate at the cryo temperatures, then you can try to, change the temperature. You can change this temperature and accordingly, because your equation also include, the thermal behavior. So a thermal part also exists in that. So if you change the temperature, then your, I mean, the characteristics will also change based upon that. Because when we are defining the barrier, then it also exists, the thermal at the normal temperature. These all properties are at the normal temperature. So if you reduce the temperature, then I mean, you need more energy, right? So the leakage current and this kind of a thing improves at the lower temperatures. Okay. Then you need to specify a substrate, like which substrate you are using. Suppose if I am talking about the MOS transistor, then I'll be using the silicon as my substrate, right? If you're using the different substrate, you can specify the gallium arsenide. If HAMD transistor, you can specify the silicon carbide. So this kind of substrate materials you can choose, okay, as per your requirement. Then coming to the crystal orientation. So suppose for the surface, if it is a surface device, then X usually specifies, that suppose you're taking a MOS device, then the surface is usually a 100 orientation. Okay, and if you are using BJTs and all, these are 111 because that's a bulk device, right? BJTs. So that kind of, I mean, you need to specify the orientation as well. What is the crystal orientation?
So this is the orientation of substrate.
Yes, orientation of the substrate.
Okay, and this is looking like cubic orientation. And what if we want to specify the hexagonal one?
If you want to specify the hexagonal one, then it will be like I guess.
There are four orientation, right? HKIL.
Ha ha ha.
Oh,
So if
there are
that also you can specify actually. So in between, like there is a syntax for that also.
okay.
Okay, for now, like I have included only like for
Cubic
I mean
one.
the 3 cubic one, right?
Okay.
Okay, so that also you can specify. Maybe
That means
later
we
on
can
I can show you that also.
between the bracket we can specify four numbers, right?
Yes.
Okay, fine.
Okay, now coming to the meshing part, which is considered to be as a most a crucial part of simulation. So wisely, that's why wisely you need to decide the meshing to reduce the simulation time. Okay. I think previously also we have discussed and explained it properly. So I'll just try to explain it again, you know, more accurately and precisely. Okay. So suppose what actually usually the meshing is specified from the grid statement. Okay. And we have you want to specify in the X dimension, Y dimension, or Z dimension that is specified by the X grid, Y grid, or Z grid. Okay. Then after that, Line you need to specify, because line is a statement to specify what is the position and what is the spacing between the 2 points.
Okay.
Okay, so this is that particular part. Okay, so let's start with this particular statement. So what it specifies is that we have a line over here, then we have a particular position which is a starting position as a 0, then in between we have a, in the second line shows that we have a point at 50,
50.
then third one we have a 100.
Okay.
Okay, by default all the dimensions are in the nanometers. Okay, also please keep that in mind. So suppose if you want to specify it in the microns, then accordingly you need to specify, you need to convert and specify. Okay, now coming to the spacing part. So what it means that, between, from starting from the 0, the spacing is 0.5. So what it means that at this particular point, maybe I draw with a different color. Okay, suppose this particular point is my 0.5, like the spacing. This is a spacing 0.5. Okay. And after that, here we talk about like 50. At 50, near to this particular point, we have a spacing of 0.1, let's say.
So 0 to 50 it is 0.5, right?
No. That's not correct. Okay.
Okay.
So starting, we have started with the 0.5. It means the first spacing from the 0 point is of 0.5.
Okay.
And 0.1 spacing means that between 0 and 50, if we go towards the 0 point, then the first point is at 0.1. Or if we go the right side, then also the first point which comes is a 0.1 spacing, is of 0.1 spacing.
Okay.
Understood?
Okay.
And similarly, like if I talk about here, then this spacing is 0.5. Okay, the first spacing.
Okay.
What is in between? Okay, in between is, just shifting from 0.1 to 0.5. The spacing will increase. Here also is increase by in between values. Suppose here it's 0.11, then 0.12, then 0.13, then 0.14, then 0.15.
It's by default. It's by default.
Yeah, it's changing. It's increasing to 0.5.
Okay.
It's linearly increasing this side. Okay, from 0.1 to 0.5. And similarly on the other side, 0.1 to 0.5. Okay, so this is an increase.
Okay.
Got that point?
Yeah.
Okay, so I would like to show from here. So if suppose like here you have a 0.1, here you have a 0.1, and in between this point you have a 0.5. So it will look like this one. Understood?
Okay.
-1, you have 0.1, 1, you have 0.1, and in between at 0, you have 0.5. Then your meshing will be look like this. Just for an example. How does it look like? Okay. You understood this point, right? Meshing thing.
Not much.
Not much. Okay. I try to explain in this other sense. Okay. Okay. So let's take an example of. Okay. Let's start with the simplistic one. Okay. So suppose we have a line here. Okay. 0, 50, 100. Okay. We skip this particular point and we mention it as 0.5. Okay. Suppose this is 0.5. Then how it will look like? Every spacing is of 0.5, right?
Right.
And how much points in between? That is 50 divided by 0.5,
Okay.
100 points.
Okay.
Total 100 points from here. Not total, it's from 0 to 50, 100 points.
Okay.
Then 50 to 100, we have another 100 points, total 200 points.
Okay.
It's understood, right?
Yes. Yes.
Okay. Now I make some changes. Now, what if in a similar way we have we reduce the spacing in between? So we reduce it to, let's say, 0.1. Then what will happen? It should change, right, from 0.5 to 0.1.
Okay.
Right, and here it should also change from 0.5 to 0.1.
Okay.
Right. Suppose it's a kind of a doping. I mean, if it will increase from the higher concentration to the lower concentration, right?
Hello, sir.
Yeah.
Sir, I have a question. Here you saying that when 0.5 is the starting point and there is 0.1. This is lower point.
Yes.
That's why
Yes.
it is decreasing and
Yes.
as
Yes.
is
Yes.
0.1
Yes.
point. But
Yes.
when you saying that this is 0.5 and 0.1 is replaced by 0.5, but these 2 points are then same. Why they then? But
Which
it
2
should
points
not.
are same?
If
You mean
we
previously
take
it was 0.5, is it?
if we take here 0.1 by replacing 0.5, so this initial and this middle point will be same that time 0.5. So this then nothing will be nothing should be happen because these 2 points are same.
No. You. Okay. Let me just describe it again. Okay. So what I mean is that when we are specifying 0.1, 0.5, okay, here, it doesn't mainly sound like, that it's a kind of a same concentration and, then it will not change, right? But another perspective to see is that you have a same concentration here, right? So what I mean is that the distance between these 2 points is everywhere is the same.
Okay. Yeah, I got it.
Okay. It doesn't mean like that it's a kind of a variation, like from the higher concentration to the lower concentration. What I mean to say is that, if there is a same concentration, then in between you have the spacing or the atoms concentration will be the same. It's just like that. It's just to describe that particular point. Okay.
Yeah, now got it. Thank you.
Any other thing in this?
No.
Balkrishna, have you understood like this
Yeah,
point?
I understand. One more thing I want to ask, like 0.5 to 0.1, how much point in between? How much point are there in between?
So that's what I was saying, that it's not like that you calculate all the points. It's a kind of a automation that in between it will automatically generate. I'm saying that if it is the same, then we can easily calculate. But if it is, different, then, at some particular point it will be, dense. At some particular point it will be loose. That is depends upon this spacing. So wisely we need to decide the spacing.
Okay.
It just mean like that. It's not about,
By
calculating
default,
and putting the values, right?
Okay. By default, it is increasing or decreasing by 0.1.
Yeah. I mean, that's a minimum spacing you can keep.
Okay.
And now I would like to show you that where you need to put a dense mesh, where you need to put a coarse mesh, how you will decide that.
Okay.
Starting from your example that is of LP. Okay. So now let's start with your LED example. That is, okay. So I just tilted the LED and specified into the, where we have a different layers and we have a substrate, silicon substrate like that.
Okay.
Okay. And now, what do you think where we should have a dense mesh? Because dense mesh will create more points, more number of points at a specific region. So I'm just drawing a cut line here with a different color, maybe. So here, like this. So what do you think that where we should have more number of points?
At the
Most
intersection.
What do you think,
node
like
size.
in between?
In between the layer.
In between the layers?
If in between the layer, then multiple quantum well having more points.
No. Oh, okay, let's take an example. Like I'm just plotting it like this
Okay.
one at a band structure.
Mm-hmm.
So you are specifying that here we should have more points.
Mm,
In the mid, right? In the mid of this particular part, right? You are saying
yeah.
that we should have more points. And what
No,
is the
no, no.
reason for
At
that?
the
What is the reason
intersection
for
of
that?
the layer.
Yeah, exactly. We are going to, this is our main part, right? That how our barrier is changing,
Right.
right? So here we should specify, because if you specify less points near to a junction, then it will, move like this or like this. Then your device functionality will change,
Mm-hmm.
right?
Mm-hmm.
You need to be more, I mean, more predictive, like more accurate in this particular region, because here your band value is changing, right? And if suppose you put a less points here, then if something it will be something like this, then your barrier width will also change, right? And if electrons need to tunnel, then it, I mean, all the the process is changed, right?
Okay.
Okay, I'll give you another example as well.
Mm-hmm.
Now you have a MOSFET.
Mm-hmm.
Everybody know about the MOS functionality right here. So let's correlate.
Mm-hmm.
This is drain, this is source, this is gate, and this is substrate.
Mm-hmm.
Where do you think that we need to specify the dense mesh? Where we should specify the coarse mesh? I mean, and why?
Between the interface, means gate and that substrate interface, and drain and that channel interface.
Yeah, correctly. I mean, you're correct about this, because here our channel is going to form, right?
Mm-hmm.
And the most, I mean, if you consider more points here, means more equations will be solved and it will give you the accurate result,
Mm-hmm.
right?
Mm-hmm.
Because if the less points will be there, then you will compromise with the accuracy.
Okay.
Okay, so in that way you need to specify dense mesh where which is a area of concern. Okay, and loose
Okay.
mesh where you don't care, right? If we talk about the silicon area, we don't care about this area
Right.
anymore,
Right.
until unless we are going for the breakdown analysis.
Right.
Okay,
Okay.
understood, right, this point?
Yeah. Yeah. Yeah.
Okay, so accordingly, this is for the 1D. Then similarly, you specify for the 2D
Mm-hmm.
here and 3D in a similar way.
Okay.
Okay, these are the example of the 2D
Mm-hmm.
2D meshing. Okay.
Okay.
Now coming to the structure, that how you are going to create, because right now you have specified the meshing, which is a outer borderline, and in between how where the you want the equation to be solved, right? So these are the points you have specified. Some of the points. Point, I mean these points. These are intersecting point where the equation will be solved.
Okay.
Okay. Now, okay, we talk about the structure, which include the region, which is specifying by the different shapes. You can specify the region, then material and doping, then after that contact. Now coming to the structural part, that is, if you have a line, then you can specify with this particular statement, okay, this is my region. Okay. How it works is, so we'll take a previous example that we have a 1 0, then we have a can you please mute yourself, please, so that I'm sorry. Maybe if you question, you can unmute yourself at that time. Okay. So we have a 50, we have a 100. Okay. Then we take a similar example that we are starting with the 10 and we have up to 20. We have a particular, line or region. Okay. So this region we have selected, and later on we'll fill the material in this particular region. And if you want to specify, different layers, then accordingly you can take the different line statements and specify your regions. Okay, in between, because you need to specify the different materials after that. Okay, so first thing is to specify the region, then in that region we'll fill a material. Suppose in this region later on we'll fill the aluminum gallium arsenide. Then after that we'll take a 20 to 30, we'll take a particular region with the gallium nitride. Then after that 30 to 40 again aluminum gallium arsenide. Sorry, aluminum gallium nitride. Okay, like that we can fill the material. So accordingly we need to specify the region statement. Similarly, for if you are talking about the 2D, okay, in that case we have I mean, in the 2D we will be having the structure like this, and we can specify, okay, my region is starting from, let's say, x-axis is from 10 to 20, and from here to here is suppose like okay, 0, maybe 0, starting from the 0 to 5, like this. I mean, we can specify a particular rectangular box, and accordingly, I mean, you can like fill the material in that particular region. And later on, similar kind of a boxes you can define to define your structure. Okay, it's just to specify a particular region where you need to fill the material. Now coming to the 3D. So this is an example of 3D. So here you can specify the circle as well by specifying that what is your x dimension, what is your y dimension, okay, and after that what is the radius. Okay, accordingly, I mean, you can specify the circle as well. I mean the x and y point, I'm sorry, this one. Okay. Okay, and this one is the cylindrical part. So if you see, like, we have a x, y, and z part here. Okay, and then we have a radius. So we have a specified, in this case, we have specified to make this kind of make just a second. Make this kind of a structure. What we have done is we have specified one particular point which is at 50, 50, and 30, and another point we have specified here as 50, 50, 60. So from here to here, it's 30 nanometer. Okay, and then we have specified a radius which is 20, right? And if we rotate this, then it will become the cylindrical shape. Okay, so in this way, you can specify your regions. Okay, any question in this?
No.
Hello, sir.
Yes, yes.
Can you please little bit specify little bit more for circle? How can you define the region for a circle?
Okay, so what we are doing is we are specific. We have a point x and y. So this will give you a particular point, right? That is 10.5 x and 14.0 y. Then after that we have a radius here that is of 10, and like this it will form a circle. Okay. Okay, now coming to the next part, which is specifying a material. So once you have specified your region, then you need to specify a material which can be specified as binary. If it is a silicon, if it is a gallium arsenide, if it is germanium, if it is any other substrate material which is not a composite, then it comes under the binary, and you need to specify like this. If it is a ternary, that which is a composite of like three elements, then in that particular case you can specify the name like this. If you have seen, the x specifies the concentration of the alloy which we are using, because here you need to specify this composite number so that it will get multiplied, and if the aluminum concentration will be larger, then your band gap will be more, so you can tune that particular part. Along with that, if you want that your concentration should, suppose we have a composite and like indium aluminum arsenide, then if you want the composition to be changed throughout the length, one particular direction, okay, in that particular case, so it's changing along the x-axis, right? So we have suppose this one. So here it will be 0.8 concentration, and then it will reduce to 0.2. So this kind of a thing is also possible by ternary underscore linear statement. So you can linearly vary throughout your substrate and check the functionality of the device later on. Okay, is it clear?
Yeah.
Okay.
So it's a linear grading kind of thing.
Yes, correct.
Okay.
Now coming to the doping. So in the doping part, actually you can specify the constant doping. You can specify the linear variation in the doping, right? In a similar like the previous we have discussed. So suppose it is increasing from 1E18 to 2E18. Okay, then you have specified, okay, this is my x-axis starting from, I'm talking about this, okay, the 50 to 100. So this way you can specify, the statement for the linear variation. This is for the constant, that throughout the substrate, whatever you have selected, you have specified a concentration of this much. Okay, then we have a Gaussian doping, which is mainly used for the the ion implantation process. So that usually create a Gaussian kind of a doping, which is having a particular peak, which is considered as a range, you know. Its actual name is a projection depth, projection range. Okay, so how is really I try to show it through the figure. Suppose okay, this is my structure, this is my 2D structure, this is my y-axis, this is my x-axis. So if I draw, if we do the implantation like this, okay, so our doping will be somewhat like this, and more doping like here. Okay, if we draw a cut line, then it will look like this one, red one. Okay, that initially we have a less at near the substrate, then when we go inside it will increase, then after that it will decrease. Okay, so this kind of profile also can be created using the Gaussian statement. So here you specify the concentration, you specify the dose, then you specify the x-axis, then the variation you can specify, the deviation, standard deviation. Okay, so what is your standard deviation? This is specified by this particular point, like from the projection range to this particular distance, then how much is the variation is there. Okay.
Can you please tell me about linear one? Sorry.
Linear one. Okay, sure.
Yeah.
Just a second.
Mhm.
Okay, for linear one, actually, what we are doing is, suppose in the y and z, we are not changing any dimension, so it's at a particular point, right? So we don't need to worry about this one. So we need to worry about the x-axis because it's a changing from 50 to 100.
Mhm.
Okay. So in that, what is happening is that at the initial stage, like x1, this is x1, this is x2. We have a value, x1 is having the value of 1e18, and then another point we are having a 2e18. So it's linearly is increasing to 2e18 from 1e18 point.
Okay.
So that's what we are specifying here in the linear statement.
Similarly, in the y and
Similar.
z also, if we are considering the same.
Yeah. Yes. It's the same. It will be distributed in y and z.
And suppose if we are doing the 2D structure, then we have to specify an x and y.
Yes. Correct.
Okay.
It's mentioned here, like if it is only for the 3D, you need to specify. Otherwise, you can discuss this particular part and use the x and y only. Okay. Okay. Now coming to the context section. So up to now, what we have done the meshing. Then after that, what we have done? Region. Then what we have done? Material. Then after that, what we have done? Doping. Right. These things we have completed, and initially we have specified the dimension of simulation, right? What particular dimension we are going to use, 1D, 2D, or 3D. Okay, so now we need to specify, because this is our structure part is almost complete, and we need to specify the context statement to, apply some bias condition over that, and then later on see the functionality of that. So usually for the context statement, actually these two statements are used, right? I mean, that is to specify. It's a simple one, like you specify the contact and then specify the name of it. Okay, and then you can also specify its dimension, okay, as well. And is okay. Another thing is remove option is only for if the region overlaps. Suppose if you have a silicon part here, and if in this particular region only you have specified the contact statement. I would like to specify with a different color. Okay, in this particular point, you have specified the contact statement. So what it will do, it will override the silicon and place the contact here. Okay, so this is just for the overlapping. Then later on, actually, this is not the part of the contact, the Schottky and the ohmic. It comes later on to specify whether your contact is ohmic or Schottky. So about this statement is that whatever the bias condition you are applying, you need to specify here and let, because usually while doing the equilibrium setup, so it start with the 0 biasing. Then for the Schottky, you need to specify the barrier height, or else you can specify the work function. For ohmic, You just need to specify that if it is a biasing condition, what is a biasing condition like initially, or I think you don't need to use shift can be okay. Definition. I mean shift I don't think so. You need to use any like this statement. So this is a basic statement. I mean you can use for the ohmic. Okay.
One question is that we can specify bias as 0, but if what is the final, how we define the final point? That means what I mean is 0 to 50. I want to go 0 to 50 volt, suppose. Then how so how we define the final point, that 50? Yeah.
So suppose we have specified this context statement, okay, in the ohmic. Then bias you can specify, then you can specify the bias start point and then the bias end point. Then after that you can specify the steps.
Okay.
Okay. Similarly, which you have specified in the LED, right? So in this way you can specify, because that time you were simulating only for the one biasing point. Okay. Okay, just a second now.
And I do not understand that remove point. That removes, you mentioned the remove in the first.
Okay.
That I do not understand.
Wait a second now. Are you able to see the screen? Hello.
Yeah.
Yeah. Okay. So what it means is that suppose you have this kind of structure you have created. This is all made up of silicon, or maybe something else is there, and in the left side or right side you want to make your source and drain contacts. One thing you can do is you can make a contact here, right? Another thing you can do instead of this, that you can make a contact within the silicon.
Okay.
Right. So what it will do, remove statement, is that it will override the silicon and make a contact at this particular location instead of this area. It will shift to this particular location. Okay, it will override the silicon. So silicon area will be, length will be reduced to only this much instead of this much.
That means initially we generate outside, then after using the remove we can make it inside.
We can overwrite on the silicon.
Okay.
Understood?
And what if contacts are top and bottom?
If top and bottom also, like suppose initially you are going to put here, but if you specify a dimension like inside the silicon, okay, here, then what it will do, it will overwrite this particular area, area of silicon, and make it as a contact, and then your silicon thickness will be like this much in this particular region. Okay, it's just overwriting that particular silicon area. That's it.
Okay.
Okay, then it comes to the models which we are going to use. So different kind of a mobility models you can use, which is specified here, like the constant mobility model, Aurora model, Minmos model, and Simba mobility model. Right. Along with that, some other kind of models are there, which are recombination models, Euler radiative models, and so these models are available inside, and by the time they are adding the new models as well, I mean based upon the testing and all. Okay, So you will get the updates like up to 3 years, so you don't need to worry about that. Okay. So another models are there, which is basically for if you're applying the high bias condition over the drain, and then the electric will be more, field will be more, then you need to specify the high field saturation. So to saturate the current, right, even in the most transistors. So these values you will be specifying in that particular case.
Okay.
Okay. Any question in this?
No.
Okay.
If anyone else having that, I don't know.
Okay. So next part is the method and the solve part. So actually from the device point of view, if we talk about these models as well, so you as a device engineer, you should know that what kind of a models you want to use to define your device functionality. Okay. For an example, that if suppose I am doing in a normal transistor, if I am doing a IDVG simulation in the at the low VD condition, okay, in the linear region. So in that particular case, which kind of a models are effective that a device engineer should know? Okay, do I need to use the kind of impact analysis models in that particular case? Because the VD is low, there is no point of using the the impactization model in that particular case. Okay, if we talk about another like hot carrier injection, do we need to use that particular model? I would say no, because the drain bias condition is very low, right? So this as a device point of view, I mean, you need to understand that what kind of a models is useful for your device. That is most important.
Okay.
Okay, now coming to the methods and the solve section. So there are two kind of models which you can use to solve the device physics. One is a classical one, which is mainly used for the bigger length devices. For example, like HAMT. I'm not talking about HAMT, maybe bigger devices. HAMT is a bigger device, but like 2D EG layer, if you need to simulate, then in that particular case, you need in that particular sense, you need to use the quantum models. Okay, but if we talk about like the MOSFET at like 45 nanometers and all, so in that particular case, also you can use a classical model to specify, to simulate the classical equations, because quantum usually takes some like more time comparative to the classical one. Okay. So actually, this is the basic statement of the classical one, and there are a few more syntaxes also there, which is available in the manual as well. So the gamma is usually specifying your band edges. Okay. Then after that, you have the different. This is for the valence band, and this is for the gamma is for the conduction, but to specify the conduction band, and this is to specify the band edges. Okay, in the output. Okay, so these are a few statements to see, and one more thing. So once you're specifying the output, it exactly means that what exactly you want to visualize in the output. So whatever the output statement you are specifying, I mean, whatever you want to visualize, you need to specify the output statement accordingly. Suppose you want to see the bandages, then output underscore bandages you need to use. If suppose you want to see the output carrier densities, then output underscore carrier density you need to use. If you want to suppose you, I mean, see the intrinsic density, that, I mean, statement you need to use. So in this way, I mean, different statements, whatever you want to visualize in the output, right? So accordingly, you need to provide the output statement. Okay, so that it will be included in when you simulate your device. Okay, and then you can visualize in the output.
So can we see the band offset and all that using can we see the band offset and all that?
Yeah, that's a part of the band edges, right?
Okay, okay.
So all these things you are able to visualize. Okay. Similar for the quantum actually. You have the region statement where you are providing the quantum statement and quantum regions you are specifying where the quantum simulation need to happen. Okay, then different kind of boundary conditions also you can specify at different points. So that is also a part. For this, to explore it more, you can also go through the manual. Okay, to explore it more, then what kind of because there are different kind of statements are there to define the different problem statement. So I have just mentioned few here. I mean, you can directly go to the manual, and because it's step by step, it is described in a proper way this time because they have rearranged all the manual stuff. Okay. If any problem comes, you can come to us. Like if in any syntax you are facing the problem, but at least you need to read it first. That kind of
Okay.
stuff. Okay.
Okay.
Then after that, it comes to the run statement. Where what exactly you want to run. Okay, whether you want to run only the structure, whether you want to run the strain current Poisson equation. Current Poisson is mainly for the coupling the current. Okay, 1 second. Coupling the current along with the potential. Okay, simply if you just write a Poisson, then it will solve the potential. Okay, and the quantum current, it solves the Schrodinger-Poisson equation. Current Poisson is mainly, I think, it's using the classical one, the classical model. Okay, then if you want to run the quantum only, then optic only. I mean, it will run accordingly. It will run some set of equations on the basis of that. So these are the statements. Okay, which you can execute. Structure, strain, Poisson, current Poisson to see like the IV characteristic you want to see, then you can use the current Poisson equation, right? If you want to solve the quantum along with the IV characteristics, then the quantum current Poisson. Okay, if you just want to see the quantum potential, then the quantum Poisson. Optical device, this is for the optical part. Okay, and yeah, this kind of a thing you can use. Understood?
Yeah.
The last part is the convergence. So you might face some of the issue related to the convergence, which is it is not able to converge the equations because in the background it used to solve multiple equations and there will be residues are there which because maybe you have heard of the Newton simulation and Newton, Gumel, and these kind of different kind of methods are there. So what it will do, it will try to minimize the error in order to resolve a particular equation. So multiple iterations will be there to solve a particular equation. So for that, it will try to reduce the potential in order to converge. Okay. Suppose if you directly apply a 1 volt bias condition over the drain, then it is highly unstable and it will face a convergence issue. Then what it will do, it will reduce to 0.5, then again it will reduce to 0.25, then again it will reduce to 0.125 in order to converge. So this is a normal process, I mean, which happens in the background. So few things you can do for the convergence is one is to recheck meshing, whether your meshing is proper or not. Another thing, this is a primary part you need to check. Then after that, you need to check your models. Second thing is models and methods. Then after that, it comes to the solve section, which like number of the iterations, then residual for me, and this number of iteration you can try to increase. Okay, so if you increase the number of the iteration, then multiple times it will try to solve that particular equation. So in this way, I mean, it helps in some of the cases to converge. Okay, then residual for me are there, which is to reduce the error time. And but once you increase the number of the iteration and this particular part, then surely your runtime will be longer. Then another some kind of part which you can mention in the method section is the alpha for me and the current iteration in order to converge. Okay, but you can also, like, you can try this kind of a things by yourself first, and if you again, like, if you are not able to solve it, then I guess you can also come to us in that particular case. Okay, related to the convergence issue, we can help you out. Okay, now coming to the different application as we have discussed. So electronics, optoelectronics, quantum cascade lasers, you can also simulate the biochips. Okay, because in the biochips we usually have an electrolyte in between, and there is ion transport between for the conduction. So that kind of a simulation can also be possible using the Nextnano software. Solar cell, as we have discussed, quantum dots. Actually, most of the people are using for the quantum dots and quantum computing. They are working on the Nextnano software. And also the QCL part is important. I mean, you can also, if someone is interested, they can also try to explore the quantum cascade laser as well. Okay. Yeah. So another thing, maybe you can note down the our emails for the support. So you can drop the email on this email ID, deepak@maximdesign.co.in. You can also drop us email on support@maximdesign.co.in. As we have discussed, they have also modified the manual section. So you can also go to the manual section and check for the related to the different syntax, what are their meanings. Along with it, they have also updated the tutorial section, and it is very, very well described over there. I don't think like you will face any issue in that to understand each and everything over there. So it's very okay. Now are you able to see?
Yeah.
Yeah. So just a little bit about the functionality first, about the software thing. So here we have the different sections, like the file section where you can have the different examples library. Okay, and here you can select the different example files, and we have the different example file for the MSP, as we have discussed, Nextnano.MSP, which is for the resonant tunneling diode and the quantum cascade lasers. So few examples are there. For Nextnano++ also different examples are there, 1D, 2D, and 3D. Many examples are there, and some of the examples which are not listed, we can also request Nextnano to provide that kind of examples. So that is also possible. If someone is comfortable in the Fortran, they can also explore this Nextnano 3. Okay. Okay, let's go to this one. Okay, so from here, we have the save input file as, so directly you can save from here, and then we have a run section here. You can directly run from here. Okay, from this, and along with that, we have okay, no need to run on this. Okay. Directly you can run from here as well. Like if you have suppose open 2-3 example files here and you want to run in the parallel, you can also run in the batch mode. all the example files. Then we have options to view. One is to view in the different output tab, or we have the to visualize it in the graph form. For an example, like suppose this one. So I want to visualize in the graph form, so it will be like this. But if I'd like to view it in the data form, it will be like this. And later on, what I can do, I can export it into the different, let's say Excel, and like plot like this. Okay. So I think you are also much comfortable with the, I guess, the origin for plotting, right? So in that also you can include the data and plot. Here also, I mean, I try to show some of the things by which you can visualize it more clearly. So I think in your system as well, Balkrishna, we have installed the GNU plot. So you can directly, this is export and open in the specific format tab here. So if you click here, then we have option of create a new GNU plot. This is for the visualization. So you can just save it. Okay, and you can label it that suppose this is my length, and this is the energy. Okay, so this way I'll just mention it here and it will open up like this. Okay, so this is for the visualization purpose, that how you want to represent your data. Okay, so this you can visualize in the GNU plot.
So it came under view, right?
Huh? Yeah, this one. This actually export and open in the specific format.
No.
In the view also, and in the view is just, I mean, it's just for the visualization, that open in the plot or open in the open in the this one. So
how much runs we can perform at a time?
You mean like parallel simulations?
Yeah.
So I haven't checked that how much you can do. Let me just try to add input file into the batch list. So I also need to test this function. I haven't tested this. Okay, you have suppose added these two files into the batch mode. So one by one it will run. So first, these two are running in the parallel. Yes. Okay. I'm not sure that how many we can run in parallel. So maybe you can explore this one.
Okay.
But that's a good function actually. I was not aware of this. I haven't used this actually.
Okay.
Okay. Then I think this is okay. It's related to the graph which is here. So in the output section. Then in the tools, we have already discussed about this active license. You can activate your activate license from here, and then this option I haven't used, but you can explore this one. This is for converting the Nextnano 3 syntax into the Nextnano++. Okay, but this is under they are checking this, so this is a beta version. So maybe they'll launch this sooner in the next stable baseline. And then this is for the cleanup, the simulation output folder. This way you can suppose clean all this stuff, delete all stuff. This will clear all your simulation outputs which you have simulated. Okay, and okay. Okay, then you have the different options. So here actually you have the material database here and licenses here. Then custom executable is the suppose any other simulation tool you want to add, sorry, visualization tool you want to add, you can add the syntax here, and it will open up for you. Okay, for the visualization later on. Okay, this is the material database.
Can we visualize the generated structure?
Yeah, sure. I mean, what do you exactly mean? I mean,
that suppose I'm drawing a 2D structure using this
yeah,
software,
yeah.
right?
So let me
And I
just
want to see whether it is properly like that I designed or not, something like this.
okay. So let's run this 2D. Okay. This is a 2D gate. I mean, double gate transistor. Okay. So in the meanwhile, we'll check this. Let's go to the structure, and there you can check the 2D structure as well. I mean, like this.
From
So
where
these
it,
are our
from,
contacts.
oh, from where it came?
This one, the structure. So you
Okay,
click on this one, the output section, then structure. Then at the different biasing condition also you can check.
Okay.
The band edges, the current electron,
Okay,
the
fine.
densities and all.
Okay, fine.
And this in the right side you are able to see the visualize it, properly. Okay. Apart from this, there is one other thing we can install, that is to visualize it in the custom visualization tool. So for that, okay, I need to check. Okay, just a second. Yeah, so we can also export this in the VTR file, which later on you can open it in a different tool as well. Okay, like ParaView. So ParaView is a tool for the visualization. Okay, so to make it, if you want like to be visualized in a different way, so let me just try to show it here. Display. Suppose you want to visualize, what are the electron concentration, electron density, in the channel part. So in this way, you can able to visualize as well.
Okay.
So this is also possible. Okay. I mean, if you don't want to, take this as an output, so you can just visualize from this one, and you can export it, and later on you can use it for the publications as well.
Okay.
Okay. So the software name is ParaView.
ParaView.
Okay, you can install this one as well. Okay. Okay. Apart from this, okay. Now we go to the tools and yeah. So you also have the Yammer thing. Okay, so you can raise your request. On this particular platform related to the software syntax. If there is any issue with the software syntax, then only you can use this one. I mean, otherwise you can come to us first. So that's a usual support thing. Okay. Okay. Now coming to this one. So I'll just recall everything. So this we have used for specifying the dimension, right? That 1D we are going to use. So this is an example of the PN junction. This is for the meshing. This is for the structure, right? And then we have the different region statement to specify the a particular region, for defining the material, right? Okay. I mean, for this one is for the doping actually. We are specifying the doping here, that okay, this to this we have this kind of doping, and this to this we have this doping, right? And then we have this is related to the impurities. That degeneracy is normally that considered as that all the impurities are ionized. Okay. I mean, usually after the thermal annealing, like all the impurities gets ionized. I mean, they are not like I mean, it will act as a trap inside. I mean, not act as a impurity. So it does mean like that, like 1000 minus 1000. Okay, then we are specifying the contact here with a particular biasing. Suppose if you want to increase the biasing condition, then you can accordingly put the statement in the bias. Okay. Then we have a simulation methodology. That classical we are using because it's a bigger device, so no need to go towards the quantum one, right? Then what output you want to see? That's for this particular statement, and we are running the Poisson equation to check the potential and this kind of carrier densities, which is specified in the output statement. So this is related to the syntax. Okay. I guess for now, I think this is okay. Maybe we should continue this one in the next session, next Saturday.
Yeah.
Right,
Definitely.
because it's I think it's too much, right, for
right
a single day.
That's what I'm requesting to you again.
Yeah, surely. I mean, we can start with the LED example in the next
LED
case.
and
Maybe
and one more photo detector also.
Photo detector, actually we need to check with them, and because once this procurement is complete, then only we are able to request for the examples now. So I think we should, for that we need to wait.
But
Okay, so
it is if it is there, then that would be very nice for me, because I'm working in that domain only.
yeah, just a second, I just stop recording.